We're going to cover solenoid actuators, which are really nonlinear systems. Now, we can linearize a lot of this stuff. That's what we're going to cover after test one. How can I take a nonlinear system and actually linearize it? So we've already covered solenoids before. Door locks are a very easy example. So I give it some kind of voltage. That creates a magnetic field around the coil, and that moves the armature or the plunger. So that's converting electrical energy into mechanical energy. You can make this really simply. I don't know if you've ever made one before. All you need is a coil of wire. You need a battery, and then some kind of iron core, something that's usually something steel to move through there. And so basically, it's very similar to a DC motor. It's just instead of doing rotation, I'm getting a translation. So what's going to happen, I think it has maybe here, is that as you put a current through there, I get that magnetic field, and the armature wants to be in the center of that magnetic field. And so that's what's going to pull it over. And then typically you have a return spring that pushes it back once the current goes away. So it's used in, like we talked about, locking mechanisms, robotic actuators, and then any kind of valves, even HVAC, dampers, you can open and close. Those are typically actuators as well. So we've seen this before. We've only focused on the just purely mechanical side where I'm looking at a force as the input. Today we're going to expand it all the way back to the circuit. So we're energizing the voltage source, producing a current, creating magnetic field. That force attracts the armature towards the center of the coil. And then again, once that's taken away, I have the return spring that's going to push it all the way back. And so that's our schematic right there, where the coil, again, is a coil of wire around the armature. So this is the simplified version. This is what we're going to be working with today for bow body. And then after this, we'll do some simpler problems. So when I'm looking at a coil, anytime I have a coil of wire, that has inductance. That's an inductor. Even though it's not, that tiny device I can just plug into it's a big coil of wire. But the inductance is a nonlinear function of the armature position X. So as the armature moves, the inductance is changing. So it's related. On the equation sheet, we have typically for a linear inductor, the voltage of the inductor is equal to lambda dot, which is the magnetic flux linkage, where if it is linear, that's just equal to the inductance times the derivative of the current, so IL dot. However, in this case right here, lambda, magnetic flux, is equal to L, the inductance, which is a function of X times the current. So our equation is going to change because it's not a linear inductor. So X affects the current. Current's going to affect X, so they kind of go back and forth, giving us our motion. So what do we got to do? Well, to solve for the nonlinear lambda, so again, I want to solve for the voltage right here. I want to solve for my nonlinear voltage across the inductor. That's equal to lambda dot. I have to take the derivative with respect to time of the first term, L is a function of X, and the derivative of the second term. Okay, so we have our solenoid, we have a nonlinear inductance. So we've got to take the derivative of both. It's the product rule right there. And since L is a function of X, it's not really, what I can do is I can use the chain rule here to break this up, take the derivative with respect to X instead. And that can get us a little bit closer. Does anyone know a good way to show this other term, derivative of current with respect to time? Anything we've done before? Derivative of current with respect to time? No, maybe? No? Nothing? All right, this is the same as IL dot, derivative of current with respect to time. So we can simplify that, make it look a little bit nicer. But for this first part right here, I've got to use the chain rule to break that up. So using the chain rule, we can take derivative of L with respect to X. Then I've got derivative of X with respect to time multiplied by the current. And then we've got this over here. And so by doing that, again, this is equal to that. Is there another way I can write derivative of X with respect to time? You got any ideas? X dot, very good. So our final nonlinear relationship, our voltage across the inductor, because it's tied to the position, I get a very complicated equation right here where voltage is equal to L, that's a function of X. So that's the derivative of L with respect to X times X dot, its velocity, times the current plus L as a function of X multiplied by the change in current, IL dot. So this is a difficult, complicated. Notice we have two different derivatives. We're typically like that. So really, to be able to solve this, now we can still use Bobati. We can still get all the way to a mathematical model. It's just after that, actually analyzing it, I'm gonna have to linearize this. I need to know kind of where we're gonna be at. We'll talk about that after test one. But being able to try to set it up as a linear equation so then we can solve using our traditional tools. Questions? Okay. So this is a definition we're going to use instead of this nice, easy one. This is great. We're going to instead use this voltage, but we're still going to treat it, Bobati is still going to stay the same all the way up to the model. All right. So if I want to draw it a little bit nicer, we can separate it into two parts. So I've got my circuit right here. This is the coil of wire. This is what's actually surrounding the mass. I've got my mass. It has a force, and we have a return spring. There's also some friction, viscous friction, which means linear friction. So let's create the mathematical model. We're going to do Bobati. And just like with the DC motor, it's good to breathe. It's good to, okay, let's take a step back. I'm going to look at each part individually. And there will be some things connecting the two. But at the moment, I'm just going to look at it as two separate things. We're just going to try to get all our definitions together. All right. Can you give me a guess what the order of the system is? First order. That's for all of it? Yeah, so for the circuit, It will be first order because I have one inductor, therefore first order. I'm going to have an IL dot. And then for the mechanical side, I have 1 degree of freedom. It goes in the x direction. So that's going to be second order because I'm going to have an x double dot. So this will be a third order system. So 1 plus 2 equals 3. And I just want to again say it's okay if you don't quite know this at the start. It's something you can fill in after the fact. It's just trying to figure out, at least I know I'm going to have 2 equations. I'm going to have one for the circuit. I'm going to have one for the mass. I don't have to try to combine it all. I can just look at them separately. All right. Everyone good? Next up, body diagram. So I do have the circuit. I can just put my terminals. These are voltage drops. I can list my current as I sub L. And that's basically our circuit right there. One loop, therefore one current. Now we get to our mass. We have the electromagnetic force pushing on the mass. We have, which way should the spring force point? This is easy now, right? To the left, as if it's going to compress if it moves positively. And if it's moving positively, friction is going to oppose it. It's a linear friction. Viscous friction. So this one is pretty easy once I set it up. Again, from the original picture, this can be hard. So trying to draw it as bodies, that definitely helps us identify some of these forces. Okay. Now, we're going to do inputs and outputs of the system. I want to look at, just like before, I'm going to separate it into its 2 different parts. So it's tic-tac-toe. I've got input, output. Here's my circuit. Here's my mechanical. The circuit input, easy, right? E in. We got a voltage. And the output is, say it again. What? Yeah. No, it is FEM. Oh, input for the mass? Okay, yeah. But I was like, it is kind of the output of the circuit. It is tied to that. We'll get to that, but that's good. What is the output of the circuit? Yeah, X. Wait, it is, yeah, so anytime I've got an inductor, that's my output for the inductor, which, by the way, we're going to get to the definition. So in case you're wondering, that is part of what's giving us that force. The more current I have, the more magnetic field I have. Therefore, I'm going to have more of a force on the mass. So FEM and current are related. And then output should be, for this one, X. We also looked at, this inductance changes, so therefore the current is going to change based on the position. So X is also going to be an input to the circuit. The position of that mass is going to affect the current. And again, you don't have to get all these. It's just trying to identify what should be in my equations. I'm going to have a circuit equation. I'm going to have a mass equation. So just trying to know what's going to be on one side, what's on the other. Questions? Okay. Next, we get to defining variables. For the circuit, let's start with some easy ones. Voltage equals R times I for a resistor. Ohm's law. What is that current? They answered, I promise. Yes, we've got the voltage, and now we're going to use that wonderful nonlinear definition for the inductance voltage, which looks like that. Isn't that nice? Okay. And after that, we've got, do we have anything else? Those are my two components, but what am I missing? Say again? That is the inductor right there. In KVL, yes, thank you. So KVL, I've got a positive EN minus ER minus EL equals 0. Therefore, we can say EN is equal to ER plus EL. Great. Okay, so this is good for the circuit. Now we do the mechanical. So mechanical, obviously I've got sum of forces equals mx double dot. I have a spring force and I have a damper force, linear damper. Fk is equal to k delta x. So we got our definitions from the equation sheet. And what can I simplify those to? Thank you. Yes, because it's tied to a wall, it's just kx and bx dot. That's it. Okay, this is good. The only problem is, now I know a little bit more about my FEM, my electromagnetic force, that it comes from the circuit that we have modeled. So we want to try to figure out what is the force. Any ideas how we can get that? Anyone have the equation sheet? At least you have a computer up. There is some helpful stuff on the equation sheet. Now, you're going to see there's not really much nonlinear stuff on homework. Every now and then, after test one, there'll be some nonlinear stuff you got to linearize. So this is definitely something new. It's a little bit hard to understand. Does anyone know how I can take, because some of the what's going on here is I have this mass that's like moving, and what we're going to be looking at is energy. How does energy give us a force? Does anyone have any past knowledge of like energy and force? There's some kind of equation maybe that relates the two. Mass times acceleration equals force. And what's energy? Okay. Kinetic energy, potential energy. Yeah, so for kinetic energy, it's 1/2 mv squared, absolutely. Energy, so the work energy theorem is energy equals force times distance. That's what they call work. So the work energy theorem is that, hey, if I have a force and I apply it over a distance, that's going to give me energy. By the way, potential energy is equal to mg, which is a force, times the distance, height. So you probably remember that, right? If I raise something into the air, I'm doing work on it because it has a force and I'm moving it a certain distance. So now I have potential energy, which is mgh, right? The higher you're up, the more potential you have. Okay, well, what does that mean? Well, this is going to be the energy of the inductor. Energy of inductor equals the force, this is my FEM that I'm trying to solve for, times a distance. What would you say the distance will be? X, yeah. Therefore, FEM is equal to the energy of the inductor, which we can call capital E, energy of the inductor divided by X. Now, the problem is that X is changing over time. So really what we're going to take is the derivative. But what I want to first give us is this from the equation sheet. So on the equation sheet, the inductor energy is 1/2 L times the current square. So that's there for an inductor. What's happening, like I've talked about a few times, but this is just actually showing it in the equation form, is that every electromechanical system passes energy from one form to another. So the way that I'm getting this force is related to the energy stored up in the inductor. The more energy I have, the more force I have. And so really it's changing as our position changes. So I'll say that's somewhat related. Really, to solve this, we're going to take the derivative of the inductor energy with respect to X because X is changing. We want to see what that relationship is. That's going to solve us what this force should be. And so we're going to take derivative with respect to X of 1/2. This is L as a function of X because it changes based on the position. Now, the current is not directly related to X, and so neither is 1/2. So I can pull 1/2 current squared, but the inductance is tied to the position. And so just like in the last equation, we can write it 1/2 L sub x. That's the derivative of x with respect to L multiplied by the current squared. That's the equation we're going to use. So we're looking at how the force relates to the energy. It's derivative with respect to position. Because that energy is going to put in some work. We need to know what that relationship is. So there it is. So we now have all of our definitions. Now this is kind of hard. I won't expect you to know how to do this all the time, right? But I've got my circuit equation, which has x dot in there. It's got L as a function of x. So that ties to the mechanical side. And then we have our mechanical side, which, you know, most of the stuff is about the same as before, but this force is related to the energy of the inductor. So now I've got this tied to the current. The more current I have, the more force I'm going to have. That's a nonlinear relationship because I have a squared term. So we can see from both of these equations, these are nonlinear. I've got variables multiplied by variables. I've got a variable squared here. So two different nonlinear parts. Questions? So much? Okay. Just put you at ease. Most of our stuff is nonlinear. But in real life, almost everything is. Wait, did I say most of our stuff is nonlinear? Most of our stuff will be linear. In real life, almost everything is nonlinear. So we have to take this, we have to do some approximations, maybe linearize it, simplify it a little bit to get it into a form we can analyze. All right. Next up, we're going to then take all these, we're going to diminish them, so we'll get two different equations. So for the circuit, I've got En equals resistor voltage plus inductor voltage. So this is R times the current plus, then we've got all of this L derivative with respect to x dot times the current plus L function of x times IL dot. And that's basically my equation. I can put my IL dot first, but it's just not gonna look very good. It's nonlinear. I still have variables multiplied by variables. I have to know, you know, what's a nominal value that I can use there to try to make this a typical ordinary differential equation. But it is still first order. My output is the current. So we have our first order equation there. Then for the mechanical, we're going to do sum of forces equals mx double dot. I have a positive FEM and then negative other two. And so this is where I use the 1/2 L sub x times the current squared minus kx minus dx dot. So we get all of our x's to the same side. And then I've got my nonlinear portion over here. This is equation 1. This is equation 2. It is still third order. It is very much nonlinear. And so we don't have a whole lot of tools to be able to analyze it unless we can linearize these nonlinear portions. Can I make a transfer function from any of these? No, because it's nonlinear. Transfer function has to be linear, single input, single output. So I cannot create it for either of these unless I can linearize it. All right, that's my introduction to nonlinear. We're not really going to cover it much in the next 2 weeks, but after test one is like, hey, there could be some nonlinear portions, so I'm going to teach you how to take something maybe similar to something like this, where I've got a nonlinear part and try to linearize it so we can analyze it further. Okay. Questions? Any questions? All right, we're going to take 5, and then we're going to do some example problems. And yeah, that's it. We'll have a little competition. Okay. So let's come back at like 8:21-ish, and we will do a quick activity.